Welcome back to Repod, the University of Solvers research podcast. My name is Andy Meir, and I'm delighted to be back with another episode of one of our amazing researchers, this time from the School of Science, Engineering and Environment. And we're going to introduce Dr. Mark Hughes to the stream. Welcome, Mark. How are you?
Hi, I'm good, Andy. How are you?
Great, thanks. Well, it's great to be here. This is the first episode of the new year, which is wonderful, just as the trimester's getting going. How are you doing? What's been happening with you?
Yeah, I'm good. Just started teaching and carrying on my research. So I've got a really exciting research project going on at the moment that we can talk about.
Fantastic. And we're back in the classrooms as well. I had my first big lecture yesterday, which was wonderful. Students were really motivated. How's it?
Yes.
It's great to be back on campus, isn't it?
Yeah, it feels really like it's getting back to normal now. So
fingers crossed.
The classrooms are very much more normal than before.
Yeah, it's been a very different couple of years. And I think one of the big challenges has been to kind of keep the research going. How have you found it? Because it's been such a difficult thing to do.
Yeah, it was really difficult, especially over COVID, where we couldn't come in. And I'm an experimentalist, so I do experiments and couldn't come into the lab and do the experiments that I really wanted to do. So a lot of it was looking back at data I already had and trying to glean out some new work from that. And there was some success with that. I did manage to get out a couple of papers over the COVID lockdowns, but it's really good now to be back in the lab and I can actually get my hands on some equipment and get some new data.
Definitely. Well, I'm glad to hear that. And yeah, I guess it goes back to sort of the origins of our research. And I suppose sometimes this moment for many people has been a chance to sort of reflect back and look at what they're doing and do things differently as well. And I know quite a few colleagues have really made use of the time to sort of think about where they're going with research, which I think is often something that's easily lost sight of along the way. And maybe just sort of kick off the conversation to sort of tell us a little bit about where you began. I mean, maybe first of all, what do you teach? What's your sort of areas that you cover?
So I teach quite a lot. Like I teach electricity, magnetism and light. I used to teach second year materials. I also teach third year photonics and nanotechnology. I do a fourth year labs on thin films. I do first year labs as well, which is kind of more general. So yeah, quite a variety of things.
Absolutely. And how did that all begin for you? So can you remember sort of the moment where you sort of thought a research career might be the path that you want to take?
Yeah, it's interesting. So I did my degree in electrical engineering at Warwick. And I didn't really consider research as a career path. I wanted to get into engineering, and like at the time, I was a little bit naive, and I kept seeing in newspaper articles and stuff that you go into engineering and there's a shortage of engineers when they've got these big salaries. And I kind of thought after I graduate, I'd just walk into a proper engineering job. And it didn't work out like that. And I ended up working in an office and realized that's not what I wanted, but it gave me the time to think about what do I actually want to do. And I decided to go for a PhD after that. So after working for a year in an office, I started my PhD at Southampton.
It feels like such a common thing, that sort of period of time to be able to reflect and think about where you're going. I always tell my undergraduate students that considering a master's is such a useful thing, because the people that I know that do it, that extra year of sort of reflecting on trying to think where you want to go with your life is really, really useful. And I think often with undergraduates, it's hard to get to that point by the end of the 3 years. So yeah, I can certainly identify with that. So you went on to then start doing your PhD. And was that a project that sort of landed in your lap, or how did you sort of arrive at the subject for your PhD?
Yeah, it was, again, it's a kind of random thing, because I know I went there for an interview, and this was at the Optoelectronics Research Centre, which is like a research centre at the University of Southampton. It was set up by David Payne, who is the inventor of a device which kind of, it's very important, but it ends up that a lot of my research is actually based around it. It's called the erbium doped fiber amplifier, and
well, that's going to need some explaining.
so not many people have heard of it, but you know that the internet wouldn't work without it. So basically, all internet traffic gets sent down optical fiber. So this is strands of glass, and the minimum loss wavelength of light that goes down that optical fiber is a specific wavelength, 1550 nanometers. But even at that low loss, after about 100 kilometers, the light has almost disappeared. So there's almost no signal left. And so what the director of the Optoelectronics Research Center figured out back in the 80s, he found that this element called erbium gives off light at exactly the right wavelength that you need to send down optical fiber. So he figured out you could introduce a small amount of erbium into a length of fiber and then excite it with a laser. And then when your weak signal comes along, that's almost died out, it goes through this length of fiber that's got excited erbium ions in it. So when this signal photon goes past an excited erbium, it causes stimulated emission. So electron relaxes back down and emits an almost identical photon. And then this carries on and cascades as you go down the length of fiber. And so you end up with a basically identical signal that went in, but much more powerful. And then this is just repeated over and over the length of the fiber. So whenever you're watching YouTube videos, it's only working because probably dozens of erbium doped fiber amplifiers have amplified the signal from wherever it's coming, like maybe in the States or something. So it was all based around the technology related to the erbium doped fiber amplifier. So I looked at a lot of different project supervisors, and the one I ended up with was a supervisor who was looking at not the same type of glass that's in optical fibers. There's a special type of glass called chalcogenide glasses. So these are glasses based on sulfur, selenium, or tellurium. And this supervisor who I actually ended up going with, he'd not invented, but he was like the main person who'd worked on a type of glass called gallium lanthanum sulfide. So it's a kind of specialist glass, but it's got very interesting and useful properties. So that's what I ended up working on throughout my PhD, was that particular glass, gallium lanthanum sulfide.
Well, it's really fascinating to hear about this. I think most people don't really know what these things are or how they work. So it's incredible to hear that technology back from the 80s is still sort of critical today. And I suppose one of the things that I wonder about that is how, what motivated you to then pursue it? Did you have a sense of this being really interesting research that mattered, or was it something else that sort of led you to think, yeah, I want to do this?
Yeah, well, I mean, I was really lucky because my supervisor both was willing and able to give me a lot of freedom in what I was doing. So I was able to go and make these glasses, basically put what I want in them. And so I was trying lots of different impurities that I could add to the glass. And I stumbled across this one called erbium, vanadium. So there's a transition metal, vanadium, and this one glass, when I tried it and looked at its photoluminescence, so the light it gives off when you shine light on it, I found it was giving off light at 1500 nanometers, so almost exactly the right wavelength that you need to send down optical fiber, but it was incredibly broad. So this is actually potentially really useful because optical fiber only uses quite a small proportion of the potential bandwidth, so the potential range of wavelengths that can go down there, purely because the erbium doped fiber amplifier can only amplify a relatively narrow range of wavelengths, because the light that comes off erbium is very narrow, covers a very narrow range of wavelengths, whereas I found this glass that gave off light at the right wavelength, but a very broad range of wavelengths. So I spent most of my time in my PhD looking at that particular glass that I stumbled across early on in my PhD, and did this to try and figure out, exactly what type of vanadium is there in the glass.
Now, people listening to this might imagine that your entire PhD was you sitting looking at glass. And I think one of the things that I've learned a lot over these years is actually that doing even that PhD level work is quite varied for many people. What was it like to do a PhD? What was the experience like for you? Did it sort of, and I think it's often a long journey for people, but was it, how did it go for you?
I really liked it. I mean, when I was doing my undergraduate, I was a little bit put off. Like I didn't enjoy it that much. I did the work and did the revision, but then when I started my PhD, I thought this is brilliant. This is what I really like. This is what I really want to do, and a lot of it was to do with the environment I was in. So my supervisor gave me the freedom to kind of look at what I wanted, and the place I was doing the PhD in was really good because it was a lot of people who were working on not the same but similar types of work. So if I had a problem, I could usually find somebody who could help me, at least to some extent, with the problem I was working on. So it was like a really fertile ground for doing research in the Optoelectronics Research Centre at Southampton.
I think it's probably one of the most valuable things that you can get as a PhD student is that freedom to explore something and dive deeply into a topic that you're fascinated by, and that I think that's how all PhDs should really be. And it's a challenge because then you've also got the burden of that freedom and constraining everything and making sure it all stays on track. But I guess at some point you got to the end of that, and was it a kind of clear transition for you upon completion? Because I think often with PhDs, it's you kind of get towards the end of your PhD, you're even at submission stage and it's waiting for your exam, and then there's that gap in between. So tell us about that transition from PhD into postdoc for you. What was that like?
Well, actually, just before I went into that transition, there was quite a major event happen. So about halfway or just over halfway through my PhD, there was a fire at the Optoelectronics Research Centre. So their main building burned down.
Oh, wow.
Almost completely. So I was right in the middle of doing some experiments on vanadium doped GLS at the time.
In the building?
Some really great data in the lab, and it was so good that I wanted to. I was working late on the Friday night, and then I went in to go in on the Saturday morning to finish it off, and then I got to within like half a mile, and all the roads were blocked off, and I could see like smoke billowing out in the distance. And found out that the building was on fire. My first thought was, oh my God, did I leave something on in the lab that caused the fire?
Yeah.
Luckily it wasn't. I'm pretty sure it was something else. It was something else far away in a different part of the building, I think, that caused it. But yeah, that was a big change. So I had to basically change direction. I couldn't do those experiments anymore. But luckily, we worked with the physics department, and the physics department had some facilities that we could use, and they had a laser called a femtosecond laser. So this generates really, really short pulses of light. So a femtosecond is 10 to the minus 15 seconds. So to put that into a femtosecond compared to a second is shorter than a second is compared to the age of the universe. So it's the pulses you get from a femtosecond laser are the shortest anything produced by humans. So you got these incredibly short pulses, but this means that the intensities that you get at that pulse can be really, really high. Although the average power is quite low, so you can put your hand in the beam and it's fine. I think it didn't hurt anyway. But
don't try that at home, anyone.
It can modify materials in really interesting ways. So what we did, we focused the light inside the gallium lanthanum sulfide glass that I was working on. So this was just pure glass, not with any impurities in. And then at the focus spot, it can modify the material in a special way, but not do anything above that until it gets to the focus spot. So it modified the material and increased the refractive index, and then you can translate the glass through the focus spot. So inside the glass, you have a region of modified glass where you've increased the refractive index, and that can guide light. And in theory, you could make three-dimensional optical circuits inside the glass by translating the glass in the right way. So I ended up doing kind of my second half of my PhD thesis on that, the femtosecond laser written waveguides in these chalcogenide glasses.
And I have to ask, because it's fascinating to hear this, how did you know or think to try pointing the laser into the glass and observe then that it modified it? Was that a sort of hunch, or was there research that informed that approach to trying something out?
People have done it before with different types of materials. You could try it on the surface as well. So people have used different lasers to focus on the surface of glasses. But I'd seen with different types of glasses, people had done these kind of buried waveguides where it's under the surface. But no one had done it in this particular glass before. So essentially my most cited paper is the one I did then on those femtosecond laser written waveguides in chalcogenide glass.
Wow, that's an incredible journey through the PhD. Certainly unusual and an incredible challenge as well. I think often we don't talk about those obstacles to completing research, which are many and varied, certainly. But a fire burning down your lab is an exceptional one for sure. So then you completed the PhD, and then where was it after that? What was your next chapter?
Yeah, well, once I was close to completing my PhD, I knew I wanted to take the opportunity to go abroad, because I realized that having a PhD allows you to go to potentially go to pretty much anywhere in the world, because you're doing something quite specialist. So if a university the other side of the world is looking at that, you're fairly likely to be able to get a job there doing that. Yeah. So I looked around and I applied for postdocs in Florida, in Australia, and in Japan. And the one in Japan came through. I got offered a position there, and it was actually a year before I actually finished my PhD. I got offered the position, so wow. I knew where I was going to go before I finished my PhD. And there's a bit of time pressure because my supervisor there in Japan kept asking, when are you going to finish? When are you going to finish? I didn't want to leave it too long in case they couldn't hire me. So yeah, I managed to finish, I think, relatively quickly given the circumstances.
It's a great way to do it. Certainly, to have a job lined up whilst you're still completing is wonderful motivation, as you say. And I think it's like you say, it does open up the world to you. I remember as a PhD student, one of my supervisors, just telling me that once you've got your PhD, the world just becomes this place that's available to you, and it certainly is. I think it's certainly partly entering into the international community of collaborators that share a common sort of knowledge of a subject. So Japan sounds absolutely incredible. So you were there for quite a few years, and what was that like as a research environment? How was it different? What was it like to be researching in that context?
Yeah, it was very different to working in the UK. So there was good and bad points. So I mean, I went there. I didn't speak any Japanese. Just arrived there. And in this country that's on the other side of the world, very, very strange. And, I felt it was, for the first few months, felt quite isolated because, especially where I was at a university called Toyota Technological Institute, which is it's really quite a small private university that's set up by Toyota Motor Corporation. And it's in the suburbs of Nagoya, which is a city in central Japan. And, Japan is quite homogenous. It's mostly Japanese people, but in the centers, not quite so. But where I was, it was all Japanese. There wasn't any non-Japanese people around, it you'd go for months and months without seeing anyone who wasn't Japanese. But I got used to that. But yeah, as a place for doing research, it was actually really good because I couldn't do anything else. I could just focus on my research.
Yeah.
And it sounds kind of boring, but I just had to focus on my research because there wasn't much else to do. But I really liked it, and plus I could go around Japan, even though I was kind of isolated and there wasn't that much to do. Just going around Japan was really interesting, and seeing Japanese people and the way Japan is just so different to the UK that I was just always excited being there. But it also meant I could really focus on my research, and I got a lot done during my time in Japan. So I managed to publish quite a lot of papers on a lot of diverse things while I was in Japan.
I think certainly the sort of international side of research is one of the really strong values and virtues of the research community as well, being able to have those experiences. And you often hear of people doing exchanges with other people from other universities around the world, which I think is a fantastic opportunity to learn about how knowledge is different elsewhere as well, and how we think about knowledge differently in different parts of the world. So fast forward to where you are now. I mean, one of the things I always like to ask people is, how do you maintain sort of motivation for research? And I think, sort of alluded to it a little bit, but what keeps you going?
I don't know. I just love physics. There's just so much to find out about it, and it's. I know someone might say, "Oh, that a physicist would say that," but physics really underpins everything. So, chemistry all relies on physics. Biology all relies on chemistry, which relies on physics. So at the base of all understanding about nature is physics. So it's always exciting. There's always lots to find out. So
and you have your own sort of kind of key priorities right now. What is it you're working on? Tell us a bit about the research project that you mentioned earlier. Tell us what you're working on.
Yeah, so for quite a while now, when I've worked in done lots of different types of research. I did this work on chalcogenide glasses. I came back to the UK and I worked on chalcogenide glasses again, but looking at electronic devices. I worked at somewhere else in Japan where I was looking at carbon nanotube devices. But when I was at Surrey, the University of Surrey, which is before I came to Salford, I was working on rare earth implanted silicon. So there are some projects there looking at rare earths, and they've got the main ion implantation facility at the University of Surrey. So that's where most of the research into ion implantation is done. And ion implantation is a really important technology because it's the technology that is used to introduce impurities in microchips. I was working on a project that was looking to introduce a class of elements called rare earths. And these give off light at specific wavelengths. So like you said, the erbium in the erbium doped fiber amplifier is one of the rare earths, and it gives off light at this special wavelength of 1550 nanometers. If you implant it into silicon, it can still give off light at that wavelength. It's a lot more difficult than when it's in glass. You have to do a lot to it to try and get the erbium to give off light, because silicon doesn't like giving off light, but you can do it. And most people had been looking at that as a photonic application. So looking at perhaps introducing optical fiber signals directly into microchips and using erbium as an interface for that. But I just had the idea that maybe this could be used for quantum technologies. So this was something that was pretty new at the time. And people were wondering what sort of material systems could be used to build a quantum computer. And there are many different ways that people have come up with for building quantum computers, and they're still hotly investigated. But I've been pursuing erbium implanted silicon as a potential way of building quantum computers for quite some time now. And there's a lot of reasons why specifically this material could be used in quantum computers and why it might be useful. So firstly, it's in silicon, right, which is really important because basically if you're going to build tiny circuits, you need to do it in silicon. The technology that's been built up over decades and decades to build the type of circuits that you find in microchips is really quite incredible. There's nothing, in my opinion, there's nothing that humans have done that comes anywhere close to the level of sophistication that you get in silicon microchip technology. So if you're going to build a quantum computer, we've got all this know-how, but it has to be in silicon because that's how we know how to build the tiny circuits. If we look at the element erbium, so it has a particular atomic structure. It's electronic orbital. So if you remember that, think of the periodic table, there's this block floating outside, and that is the rare earths and actinides, and that's because they're made of the fill up the f orbital. So all the transitions that occur, the optical transitions, and you can get magnetic transitions, this all occurs in the f orbital, but you've got orbitals that are already full that surround it. So you've got this atomic scale shield that goes around the rare earth elements, including erbium, and this shields them from the environment. And this is really important because one of the main things that you need to do when you're building a quantum computer, so you base your quantum computer on qubits, so some individual quantum system, and you want to shield it from the environment to stop what's called decoherence occurring. So decoherence is where something from the environment leaks in and interferes with the quantum state that you've set up on your qubit. So already erbium itself is ideal in that respect, and it also then gives off light at 1550 nanometers, the exact wavelength that we need to send down optical fiber. So if you wanted to communicate between two quantum computers, for example, then really using the fiber optic network at 1550 nanometers is pretty much the only practical way of doing that. So erbium could do that, and we were implanting it as well, which is the technology that is used in silicon microchip fabrication. So there's a lot of reasons why this was important. So I've been pursuing this and doing lots of different experiments on erbium implanted silicon to try and see if it's actually could be used in quantum computers.
It's incredibly exciting to hear about this research, and I wonder how you connect all this kind of quite fundamental activity around trying to realize the design principles around a quantum computer with the eventual sort of applications. I mean, do you think about those things? Do you think about what this could be used for? Is that something that's in your mind, or is it a bit more abstract for you?
Yeah, so I've been pursuing erbium implanted silicon because it's not just a gut feeling. There's a lot of good reasons why this could be useful for a quantum computer. And I've been thinking about, what the actual applications might look like. And there's something really exciting that's happened quite recently that's kind of changed my idea of what the eventual application could be. So up until recently, I'd envisaged the way erbium could work in a quantum computer as being, you'd have some tiny device that was patterned onto a silicon microchip. So these types of devices are already being looked at work on a quantum level, so that they're so small that they can pick up quantum effects. And you know, I was envisaging trying to implant an individual erbium atom into one of these devices, and then the erbium atom would form the qubit. And if you can get erbium atoms close enough together, they can couple together and be entangled. So I was kind of envisaging something like that, where you've got individual atoms in basically an electronic circuit. It would need some magnetic field in there to give you the spin states that could potentially then interact with these electronic devices. But it would basically be an electronic circuit with some individual erbium atoms implanted in the right way. But recently, there's a company called PsiQuantum who are looking to build a photonic quantum computer. So, like I was saying, there's a lot of different ways that people have been looking at for building quantum computers, and photonic quantum computers weren't really considered by the community as being that viable until quite recently. So they've been around for a long time, but you know, the photonic quantum computers use photons of light as the qubits. So it's not an atom that is forming the qubit. It's a photon that's flying around at the speed of light that is your qubit. So it's very different in these respects to other types of quantum computers. But they, until recently, worked using like fiber optic networks. So you could have some single photon source that would generate a single photon, send it down some optical fibers. It could go through a beam splitter, and you could have some phase shifting and then some single photon detectors. But you could have then a 1 or 2 qubit device that took up a whole table, because it was just these lengths of optical fiber and these relatively large devices. And so people weren't really considering it as something viable for building a large scale quantum computer. But this company, PsiQuantum, they're basing their design on silicon photonics. So that's building optical circuits in silicon rather than using silica fiber waveguides. And they're using the same wavelength of light that erbium emits at. So they're using this 1550 nanometer light, because silicon can transmit light at that wavelength as well as silica glass. And you can pattern waveguides, so channels for light onto a silicon circuit. And again, you can do just have the same principles of the fiber optic network, where you have a single photon source, send it into a beam splitter, then have a couple of channels with something to modulate the phase with in a Mach-Zehnder interferometer. And if you scale that up enough, you can have quite a few qubits, but you kind of get to a limit still. Like the size still gets relatively big on a chip. So you could have maybe like 30, 40 qubits. And then it starts getting tricky. You start getting this big mess and tangle of waveguides sending the light around. But what this company, PsiQuantum, have figured out is that you need to entangle these states on the waveguide. So you set up a state with your single photon sources, and these single photon sources then send individual photons down this network of waveguides, and they're entangled using these beam splitters. So you've got this set of entangled states. You've got this set of entangled states, but it's limited. So what these guys at PsiQuantum have done is they've said, okay, we'll take an individual photon from one of these states that you set up and send it down a length of optical fiber. So that's creates a delay in there. So it takes time for the photon to go down that length of optical fiber, and then it will come back and interfere with the states that you've already set up. So you can entangle these states in time. You can keep repeating that, and they think they can build up to a million qubit quantum computer using this method.
So this sounds very much like the end points of this are remarkably more powerful computers that can do as yet perhaps unimagined things. Is that sort of how you connect it with the possibilities?
Yeah, I mean, the possibilities for quantum computers are really exciting.
Yeah.
I don't think most people would say they're more powerful. So quantum computers can potentially solve problems that classical computers can't. And there's so many of these problems that people are starting to realize now. So right now, even though there isn't a practical quantum computer that's been built yet, people are looking at all the different problems that could potentially be solved by quantum computers once they're built.
What sort of thing? Give us an idea about what sort of thing you think they could for. What are people excited about?
Yeah, there's so many different things that you could, these problems that you could solve. So there's problems in protein folding. It covers finance, AI, everything where there's you have a big parameter space of lots of things that need to be solved at once. That a quantum computer would be really good at solving that.
I mean, it's just fascinating. I think I could talk to you all day about this subject because it's just mind-blowing, and it's just so clear how much of an impact it will have on almost every aspect of our lives. And yeah, it's great to hear the journey as well into it. So yeah, unfortunately we're out of time, but Mark, I wish you a lot of luck with the research. It's great to have you in our company at Salford, and I look forward to seeing what comes next for you. It's an exciting time to be doing research, I think, and especially when you have people like yourselves that work across disciplines and are able just to make it so clear as to how important this is to develop. So thanks so much for being here, and I look forward to seeing you around campus sometime.
Yeah, thanks. It's great for talking to you.
Take care, Mark. Bye-bye.
Cheers, bye.